Hi, and thanks for watching another in a series of videos where I've been building experiments from Charles Platt's excellent introduction to electronics, Make Electronics, and it's the third edition that I've been using. So in the previous four videos, we've been exploring the interaction of magnetism and electricity in generators and inductors. In this experiment, the book shows how an inductor can be used in a very practical experiment to build a radio receiver. Not just any radio receiver, but one that works without any external power source whatsoever other than the radio signals it receives. This very simple form of radio is what used to be called a crystal radio because a key component was a crystallized mineral like galena or pyrite. For the author's design, though, the crystal has been substituted by a diode, but the same principles apply. Before you dive in and build this experiment, one thing you should be aware of is that the primary audience for this book is the North American market. And this radio has been designed to receive transmissions from analog AM, that stands for Amplitude Modulation, radio stations in the United States. And that does mean that if you're located in another part of the world, it might not work as well for you. And that is going to depend on how many analog AM radio stations are still operating close to you. In the UK where I am, for example, this is a bit of a problem because there are very few analog AM radio stations still operating. Most have now switched over to an exclusively digital audio broadcast service. That being said, I'm still going to go through the build process and who knows, maybe we'll get lucky. But before we dive into building, it first helps to explore a bit of theory about why the radio is constructed the way that it is. Let's start with the antenna or aerial. Now, in its simplest form, an antenna is simply a length of conductor connected to the transmitting circuit at one end and open at the other end. And when an alternating current is present in the antenna, it emits radiation in the form of electromagnetic waves. The frequencies present in those waves will match the frequencies present in the electrical signal. Now those waves will begin propagating outwards. How strong the signal is and how far it will propagate is determined to some extent by the power of the electrical signal in the antenna, but other factors such as the length and shape of the antenna, the frequencies present in the signal, obstacles on the ground, the curvature of the earth, and even the weather and time of day will also have an impact. So if those radio waves pass by another antenna, they will generate a small amount of current in that receiving antenna. Again, the shape and size of this antenna are important factors in how well it receives radio waves at different frequencies. If we want to broadcast somebody giving a speech, let's say, it's surely just a matter of converting that speech to an electrical signal and then transmitting it from an antenna, right? Well, no, it's not quite that simple. And to understand why, let's assume we start by trying to do that and transmitting just a single frequency in the audio range. Let's say the frequency of the note middle C, which is 261.63 Hertz. If we graph a constant tone at a single frequency, it takes the form of a sine wave. A single cycle is the period from when the wave crosses the center line, representing 0 volts, in the positive direction, to when it returns to the center line from the negative direction. 1 Hertz means one of these cycles happens every second. So for our tone at 261.63 Hertz, there are 261.63 of these cycles happening every second. An important parameter that's related to this is wavelength. Imagine this wave traveling past a single point. And let's say we're able to note when the start of a cycle passes this point, and we note again when the end of the cycle passes the same point. The wavelength will be the distance between that point and where the start of the cycle is now. And you might be thinking, well, Each cycle lasts only 1/261.63 part of a second. That's a very short space of time. So how far could it have got? But bear in mind that this is not a sound wave. It's not travelling at the speed of sound. It's an electromagnetic wave, and that travels at the speed of light. So if we do the maths, our wavelength in this case, which we get by dividing the velocity of the wave by the frequency, is a little over 1,145,864 meters, over 1,000 kilometers. Now, if I tell you that to be effective, the length of an ideal transmitting antenna must be proportional to the wavelength, and it's commonly a half or a quarter of the wavelength, you should begin to understand why it's impractical to broadcast audio frequencies directly. Having said that, and as an interesting side note, submarine communications are sometimes transmitted at very low frequencies, but this requires very specialized antennas that are several kilometers in length. But there's another issue. Even if it were practical to broadcast and receive at audio frequencies, it would mean you'd only ever be able to receive one broadcast at a time, at least without them interfering with each other. But in reality, we want to be able to receive multiple radio stations. The solution to both these problems is to generate something called a carrier frequency. This is a sine wave at a much higher frequency. For example, a typical frequency used by an AM radio station in the UK would be 1215 kilohertz. That's well above the audio frequency range, which extends to only 20 kilohertz. And it also has a much shorter wavelength. The original audio frequency is now used to modulate this carrier frequency using something called amplitude modulation. And this means that the strength or amplitude of the carrier wave changes to reflect the amplitude of the original audio wave at any particular point in time. Now, because the modulation is working on both the positive and the negative parts of the cycles of the carrier wave, you can see that the original signal is actually reproduced twice, once on the upper part of the carrier wave and a mirror image of it on the lower part. Using the carrier wave has effectively shifted the audio frequencies into another part of the electromagnetic spectrum. So we can now have multiple radio stations operating at the same time, provided that each is allocated a different carrier frequency and that those frequencies are far enough apart that they don't interfere with each other. So now we know the form the radio wave takes. How do we go about receiving it? Well, of course, we'll need some sort of receiving antenna. And the book suggests using a simple length of 16 gauge electrical wire between 50 to 100 feet. That's roughly 15 to 30 meters. And it must be suspended as high above the ground as possible, ideally not coming close to any large metal objects like drain pipes, garden sheds, or metal clotheslines. The next thing we'll need is a good earth connection. Now, this is important because it provides a return path for the electrical current in the antenna. And the book suggests that you can use a metal pipe that's earthed, for example, a water standpipe in your garden or yard. Alternatively, you can obtain a copper metal spike like this that can be driven into the earth. Although, of course, if you are using one of these, please do be careful that you're not about to drive it into buried mains cables or water pipes. Okay, so now we have the means to receive radio signals, but we have another problem to solve. If you have several radio stations in range, the antenna is going to intercept the frequencies from all of them. And if you want to listen to just one radio station, then you need a way to filter out the frequencies you don't want. Well, fortunately, we can use something called an LC circuit, which has an inductor, that's the L part, and a capacitor, that's the C part. And depending on the values of each of these components, this circuit will resonate with a small band of frequencies and will attenuate frequencies outside this band. So this is where our inductor becomes important. Now, the author's design uses a coil wound round a plastic bottle, like a pill or water bottle. And he then puts periodic tap points into that coil. These are places where we can attach the other side of the circuit so we can easily create coils of various lengths. And this acts as a rudimentary tuning mechanism. Okay, so that takes care of the inductor. But where's the capacitor in this circuit? It looks like there isn't one. Well, actually, there is. The antenna and the earth effectively form a capacitor, with the antenna forming one plate and the earth the other. However, we, of course, have no control over the value of this capacitance other than perhaps choosing a suitable length for the antenna. So this does limit our ability to fine-tune our LC circuit. But we've sort of solved our problem. We're now receiving a much narrower range of frequencies. Now, the ability of a receiver to tune out unwanted frequencies is known as its selectivity. And you should be aware that the selectivity in this receiver is low. You might still hear overlapping transmissions from multiple radio stations. Remember from earlier that the signal was reproduced twice when modulating the carrier frequency, once at the top edge of the carrier waveform and a mirror image at the bottom edge. Now, when you mix two waveforms together, the amplitude of the resulting waveform is found by summing the amplitudes of the two input waveforms at any particular moment in time. Now, given that the amplitudes of the two copies of the original signal are both identical, except that one is positive and the other negative, adding them together is always going to result in zero. In other words, if we keep both of them, they will cancel each other out. And this is where the diode comes in. Remember that the diode will only allow current to pass in one direction. And this has the effect of eliminating the negative half of the waveform, leaving us with just a single copy of the original signal. We're not quite done yet though. The carrier frequency is still present. Well, fortunately, we can rely on our earpiece to take care of that. The earpiece is designed to respond to audio frequencies. Its physical construction means it can't oscillate fast enough to reproduce the carrier frequency. So in effect, the earpiece is acting as a filter, smoothing out the carrier frequency to leave us with just the original audio frequency.
So, as promised, even though I wasn't confident that there would be analogue AM signals to be had, I went ahead and built the basic radio. I started with a 3D printed former instead of the plastic bottle and used that to make the coil. I then borrowed a friend's garden to erect an antenna and try out the radio. Sadly, as I suspected, I was unable to receive anything. I did subsequently try hunting for analogue AM signals with a powered software-defined radio, and even with that, the available signals were just too weak to be readable.
So I do hope that you found that interesting, even though I wasn't successful in being able to receive an actual signal. As I say, if you are in the UK like me, you may well struggle because of the lack of remaining analogue AM radio stations in this country. But there are still one or two dotted around, so it's possible if you are within range of one of the transmitters that still has that service, then maybe you'll get something, and I do hope that you do. Other possible sources of AM signals in the UK are amateur radio bands, although to be fair, these days most radio amateurs prefer to use something called SSB or single sideband. That's like an AM signal, except that the carrier signal and one of the sidebands are suppressed. And the reason that they prefer to use this is because A, it takes less power to transmit, and B, it's a better use of the available bandwidth because it takes less bandwidth than a full AM signal. It's much fairer to other users of the available bandwidth if you can constrain the amount that you're using for your transmission. So unfortunately, an SSB signal is not going to be detected by this particular crystal radio. So while the signal will be received, you won't be able to hear it, unfortunately. Other possible sources in the UK for AM signals are some citizen band channels, although again, you might struggle to get any activity there. You might also stray upon non-public uses such as air traffic control, but do be aware that listening to air traffic control radio signals in the UK is illegal. The chances of you being prosecuted for it may be slim, but you should be aware that it is, strictly speaking, illegal, so probably best avoided. Okay, that all being said, I do hope that you do have more success with it than I did. And if you do, please do comment and let me know what it was that you managed to receive. I'd be very interested to find out. So in the meantime, it's now time to say goodbye to the world of inductors, at least as far as this book is concerned. And in the next video, we'll move on to the first experiment of the final topic of the book, which is digital electronics with microcontrollers. Very exciting topic, and I do hope that you'll join me for that. See you then.